Hi, everyone. Thanks so much for joining us today. I'm Allie Van Est with littleBits, and I'm really excited to host today's research webinar on choosing tech tools that build confidence early. Chances are when you were young, you learned about circuitry through a light bulb, a 9-volt battery, and alligator clips. Today, we want to talk about whether that was really the best way. Dr. Kylie Peppler and PhD candidate Naomi Thompson are here to talk about their new research on how changing the tools and materials in today's learning environment can help broaden participation in STEM, particularly among women and minority populations, and also improve overall learning outcomes. Before I kick it over to them, let me do a quick introduction. I'd like to introduce you to Dr. Kylie Peppler. She is an associate professor of informatics at the Donald Bren School of Information and Computer Sciences at the University of California, Irvine. Dr. Peppler is an artist by training. She engages in research that focuses on the intersection of arts, computational technologies, and interest-driven learning. In addition to serving as the director of the Creativity Labs, Dr. Peppler is the Chief Learning Officer at Collective Shift, the former lead of the MacArthur Foundation's Make to Learn initiative, and a member of the 2016 and 2017 National Educational Technology Plan Committee, which was sponsored by the U.S. Department of Education. Naomi Thompson, also on this webinar, is a PhD candidate in learning sciences and a graduate research assistant working in the Creativity Labs with Dr. Kylie Peppler. Coming from psychology, education, and arts, Naomi's interests include learning in informal spaces such as museums and libraries, hands-on learning, and utilizing activities such as crafting and making to encourage support for more equitable participation in STEM fields. We are so excited to have Dr. Peppler and Naomi here today to lead today's webinar. As they're presenting, please feel free to type any questions into the chat box on the right-hand side of your screen, and we'll answer them as part of the Q&A at the end of the presentation. Without further ado, I will turn it over to Dr. Peppler and Naomi.
Wonderful. Well, it's our pleasure to be here too. I mean, this is so fantastic to be here with all of you and to share some of the research that we've been doing that has really shed a lot of light on how kids learn, but how they learn with littleBits. And so it's really exciting. Naomi, you want to say hello as well?
Yeah, hi. Thanks so much for having us, and we're really excited to be in conversation with all of you. So we were paired with littleBits in part because it was just a casual conversation. We were sharing some of the research that we were doing in our work. Just a moment. This is me. I think you've already heard a little bit more about my introduction, and we'll be talking more today, but certainly feel free to click here or go to kpeppler.com or creativitylabs.com, and you can see more about what we're up to. So we've been engaged around arts and creativity and how to explore making that really matters for the learning process. So some of the work that we started going into as we started embarking on this research was to first examine the effectiveness of the types of toolkits that educators are utilizing to teach circuitry in elementary schools and classrooms. So this was not, some abstract problem that was in the research field, although, it's shared by the research, but this is a problem of practice. I was out there talking to a lot of educators, talking to administrators. There's a flood of new toolkits hitting the market at different price points. Where do they spend their money and why? And, it occurred to us that actually there's no research on this, that nobody's actually there helping you to make those decisions and to make them informed. And so we started on this line of research, and we actually uncovered a lot of things that were quite unexpected. So we're excited to share those with you today. And then our second goal was to really, how to make these toolkits work for students in grades 2 through 8 today. So what do we do to sort of promote better learning? We don't just teach things in a classroom because it's important for classroom purposes. We really want to prepare kids for a lifelong learning endeavor where they could take this understanding of arts and engineering and apply it to a variety of fields. But this is a whole sticky problem that we're going to get into where the kids really didn't know how to apply this information.
So this might look kind of familiar to many of you. So you might have experienced this in your education, or you might have started to use these kinds of methodologies in your own classroom. And this is very similar to the kinds of toolkits that I had as a kid. Where a lot of times I had a 9-volt battery, I had a light bulb, I had some alligator clips, or maybe I had some wiring. It's also not that different than what you might see in many science museums today and what kids are playing with. For years and years and years, researchers had sort of looked at the field, and they had looked at these folks that are entering into college. These are undergraduate majors in engineering, undergraduate majors in physics, and research on these populations starting in early 1960s to sort of present day has shown that these folks who are majoring in these areas still didn't have a basic understanding of circuitry. They didn't know things like current flow and polarity and all of the basics that'll be important there. And I'm sorry, we just had a... And so these issues, a lot of times when we see this kind of problem and that kids don't have this sort of persistent problem of practice, so that the instructors, what we'll do instead is we don't address it. Instead, we'll try to be better instructors. We'll try to talk to this more. We'll try to explain things, and we'll sort of build complex topics on top of these kits. And so these kinds of issues could start as early as elementary school, where teachers are expected to teach things like traditional circuitry. You'll see this in your standards, for example. And oftentimes, as we're doing this, we're teaching these with traditional toolkits. It's clear that we try to talk to these concepts about current flow, about polarity, and we expect that the kids will know them. But what we're finding is that these toolkits actually weren't designed to be able to share, to be able to strengthen these concepts. I've got a small problem with my window has disappeared, folks. So hold on, hang in there with me. I'm just going to re-share my screen. Hold on just a moment. Here we go. So, as we were saying, that all of these kind of traditional tools that we've been using, we started seeing by the times that kids had arrived at sort of their college education, all of a sudden, they don't know any of these concepts. So these are kids that are showing interest. These are the kids that that seem to know these concepts. These are the kids that get the light bulbs to pop up. And what also happens is that this creates a misrepresentation of the world that we live in. So this has an impact on the world that further down the STEM pipeline, for example. So we also know that these kinds of toolkits lead to a disproportionate number of men going on, to STEM undergraduate degrees, particularly in engineering. This is 84% of working professionals in science or engineering jobs in the U.S. today are white or Asian males. Even though more women than men earn college degrees every year. So it's just a really hard problem that we're trying to solve. So we've got this problem on the one hand where we've got this problem of learning, and then we've got this problem of participation on the other hand. And so as STEM careers become integral to the future of work, we need to do all that we can to attract women to STEM early. So we started rethinking our toolkits for two reasons. I mean, one was they were never great to begin with, but two, these toolkits, we're wondering if the kinds of tools that we use actually matter to inviting new people into the field. And we're actually finding out that the answer to that is yes on both accounts. So what we wanted to do, we weren't out to villainize the traditional toolkits initially. What we really wanted to do was just say, hey, look, you know, the maker market has brought all sorts of new tools to the fore. We've got littleBits, we've got squishy circuits, snap circuits, the LilyPad Arduino is on the market. You know, so lots and lots of things. And I'm sure you're thinking through, man, there's just every year when I go to the Maker Faire, every time I do a web search, there's always new things that are on the market. So our initial goal was just to say, hey, are all of these toolkits actually doing at least as good of a job as the traditional toolkits? Maybe, maybe not. So we started looking at all five of these toolkits and kind of making some comparisons. So I'm going to invite Naomi to kind of share a little bit more about the research study that we conducted amongst these.
Yeah, sure. So in this particular research study, we were trying to see, as Kylie said, what are the strengths and weaknesses of these toolkits? Do kids learn as much with other types of toolkits as they do with traditional kits? So in an after-school club, we broke sort of students in a range, like we said earlier, from about 2nd grade to 8th grade. We broke them into 5 groups, and each group sort of had a workshop experience with one of these kits. And we designed all of these experiences to be as similar as possible. The real only difference was the type of materials that they were using. And so each of the groups played with just one of these kits. And so there was a littleBits group and an e-textiles group and a snap circuits group, for example. And so in these groups, each participant took a pre-test and a post-test. And we'll talk a little bit about that soon in a minute. But essentially, we asked them to use stickers to show what a complete circuit would look like. And so we wanted to see if they could demonstrate understanding of circuitry, not only with the kit that they had done a workshop with, but also with other kits. And so we wanted to start to see if the circuitry experience and understanding would transfer to other types of materials. And then we wanted to see what tools supported that sort of transfer better. And so you can see here some examples of what some of these sticker tests looked like. And I'm going to talk through a little bit sort of what we were testing for and how we were scoring these things. And so we had previously identified some circuit concepts that we thought were extremely important and were also sometimes mysterious to some of those physics students that Kylie was talking about earlier. So these 3 concepts that we really focused in are polarity, so essentially just the negative and the positive side and making sure those are aligned. Connections, essentially where the conductive points of the circuits meet and come together. And then also current flow, so that there is a pathway for the energy to flow from the battery through all of the components in the correct order and back through the battery. So also, just as a side note, the traditional kit that we might have used in schools with the light bulb and the battery, usually this bulb does not actually have polarity. It doesn't matter whether you connect one side to the negative side of the battery or to the positive. And so in that case, we actually had to score items about the traditional kit only on 2 points because polarity is actually less of an issue there. So here you can see some examples of how we might score for this. You can see first with the traditional kits what a complete circuit would look like and how we would score that well. You can see that the lines sort of go really closely to the conductive points of the light bulb and of the switch and of the battery there. In the next one down below that, you can see that they drew lines that don't really connect all of those conductive points. So we would give that a 0 for connections, but they would get a point for current flow because they were understanding that loop shape. And then the third one there, we might have some discussions about on our research team. You can kind of see some of the decisions that we needed to be making. That this student, or here, there wasn't a loop, and so we wouldn't give that a score for current flow. Some of the connections are strong and some of them are not, and so we would have to have a discussion on how we would score that. Similarly, you can see what littleBits looks like. These are stickers again. You can see what it would look like for someone to get all 3 points, for someone to get no points and sort of have their polarity out of order, that kind of thing. You can see that they might put the stickers too far apart, and in that case, we wouldn't give them a point for connections. And then you can also see if they were, thinking about putting the switch sort of in the wrong order. It matters where that switch is for it to whether it would actually turn the light on or not. So we would also have discussions about current flow on that item. And so this is just some examples of what we were looking for and how we were sort of measuring circuitry understanding with these kits and with these sticker tests.
Yeah, thank you, Naomi. So part of what we knew and understood is all of the ways that the field was like testing for these big ideas was through giving them the 9-volt batteries and the light bulbs and the tools and materials and asking them about these circuit diagrams and saying, would this work or would it not work? And so oftentimes these are multiple choice tests. These are, drawing a circuitry diagram and so forth. But, the funny thing is that they never asked the kids to apply any of this understanding to anything other than the tools that they had experienced things with. And still there was no change in this work. Naomi, why don't you tell them a little bit about, sort of what we found, the sort of tale of two kits. So, how did this group and the traditional toolkits do, and how did the littleBits group do?
Right, and so it was fascinating to notice that students who were in the kit group, the traditional kit, where they played with, the light bulb and the battery, like you might have done in school, actually had a harder time, not only a little bit of a harder time on their own kit, but also with the other ones. And so they, especially with polarity, since they didn't have to pay attention with polarity, with that light bulb, they didn't have to connect the positive side of the bulb to the positive side of the battery, for example. They also weren't paying attention to that with other types of materials. They didn't really realize that that was something so crucial. And so it started to come out that this kit that we've always been using wasn't really even the strongest learning games. Students who participated with the littleBits kit actually were doing really well on items like polarity and connections with their own kit and also outside of it.
Yeah, we want to tell you a little bit more about that, but I just want to underscore, for years and years and years, this is decades of work that we've been buying these kits and using them in the classroom, for example, and still, this is immediately after the kids are playing with the kit. Can they show us that they've learned anything? And the answer was no. But with littleBits, the answer was yes. And so, Naomi, tell us a little bit more about what that looked like.
Right. So like I was saying, students in that littleBits kit group, we expected pretty much that everyone would do pretty well with the stickers with kits that they played with. And for the most part, we found this to be true, although kids in that traditional kit group did struggle a little bit more. The kids in the littleBits group did really well with the littleBits stickers, but then they also did really well with stickers of other kits. In particular, some of those other popular kits that are on the market, such as snap circuits, which is, where all the pieces sort of snap together on a board, and then also squishy circuits where we used Play-Doh sort of as a conductive material. Kids in the littleBits group did really well when they were placing the stickers and making the connections with those other types of kits, even though they had never seen those kits before. So we found that really interesting. We also noticed that they were really good at looking for polarity and then also the current flow. And so they were really paying a lot of attention to making sure that there was a loop from the battery to the components and back to the battery, and also aligning all their positives and negatives. And so those particular constructs, we noticed that the littleBits, kids playing with littleBits were noticing these in other types of materials, even ones that were completely, brand new to them. And so we really, this prompts us to look more closely at littleBits and sort of what are its affordances and why is it really supporting kids and noticing these really important circuitry concepts.
Yeah. and you know, it wasn't just that Little Bit scored well, it was really one of the most effective toolkits for really sharing this understanding. And so this is probably resonating with you as an educator. You know, you're probably remembering your experiences with the kids and sort of how they start to translate what they're doing with Little Bits, even at the very simplest level, really understanding that sort of those ideas. And so as you speak to them, it's underscored with how the kit is constructed. So Naomi, tell us a little bit more about what happened to the intervention. What's the kind of, you know, sort of in Little Bit style, it wasn't just like, you know, kids were just learning circuitry, but this was actually a whole workshop that was designed, you know, to do the circuit and then build a project around it. So say a little bit more, what are the kinds of projects that the kids were creating?
Yeah, absolutely. We wanted really the materials to be what was different in each one of the groups. And so we made sure that kids had time to also craft and to build a project. You could see we brought in a lot of recyclable materials like cereal boxes and paper towel rolls and those kinds of things. And kids were, you know, using scissors to make light up igloos, and they were making flashlights, and they were making, you know, all sorts of different types of projects using these materials, really using their imaginations and trying to not just make a circuit to have a circuit, but make a circuit that could sort of serve a purpose, or that could tell a story. And so we spent a lot of time, just as much time on the sort of crafting and project making aspect as we did on the sort of circuitry project, because we were trying to make sure that this was a different type of experience than school. And so it wasn't a lecture, or we weren't really sort of, you know, making them memorize any types of vocabulary words or anything like that. But what they were doing was really engaging hands-on and sort of working in an interest-driven way towards projects that they wanted to make and they wanted to see in the world.
And this is important to us as researchers, but it was also important to our educators as well, is that, you know, it's not just about getting kids to understand the science, right? It's about how the arts and the sciences come together. And, you know, that's at the core of the design mission of the Little Bits kits as well, is to really engage the kids in their interests, make it so that the kids can build on these Little Bits and kind of extend it through their paper craft and construction play. So all of that became really important. What we oftentimes hear from people is, you know, the reason they choose the traditional toolkit, or why they tend to cut, you know, sort of the artistic, crafty components out of there, is that eventually they feel like, well, that's distracting them from the content. It's just, you know, it's no more than you know, sort of deciding whether the box is going to be pink or purple. These kind of like very surface level engagement. But Naomi, that's not true, is it? So how do you start to understand sort of the relationship between the arts and science here? What do you start to see there?
Right. Well, we see with these kits is it really gives the students a chance to think about what is something that they would like to see and be able to like to have. And we find that the highest learning gains and the most engagement really comes when this making activities and the sort of circuitry concepts are happening at the same time. With the traditional kit, it was actually really difficult for a lot of kids to think about what type of projects they would want to make. They would make their circuit, and then once their circuit was finished, they would think, okay, well, what can I add sort of on top of this? Whereas with Little Bits, it's a lot more integrated, and it's about like, how do I make this circuit so that it works in a certain way and makes the type of project that I want it to make. And we really find when those things are intertwined, that's when we see the most engagement and the most learning.
Yeah, the science gets more complex. I mean, I love it.
Right.
I love this image here because you can see exactly what that means, is that the circuit is no longer simple, and all of a sudden it takes an interesting path. The complexity of getting, you know, the push button switch and the LED exactly where you want it to accomplish, you know, sort of the aims of the project, sort of both the designerly, the artistic and aesthetic components, but also the you know, it needs to function, it needs to work. Sort of the science and engineering components of all of this work. So all of that, I think, is just to underscore, you know, what you're doing with Little Bits and what you're doing in the classroom, or, you know, in your out of school sessions. It's just so important that you continue to allow the kids to not only just learn and engage in the science of it, but also to keep building those projects. So what makes littleBits more effective than other sort of toolkits on the market? And so we want to share a little bit about it and sort of the design sensibilities. So it was really fun, you know, kind of hearing from the designers like, oh, wow, that was something that we worked really hard to make sure was in the toolkit, was some of the things that actually made it great for learning. So there's these things where, kids aren't just learning about littleBits. It's not just a toy that's sitting in front of the kids, but they're engaging in this sort of conceptual understanding of circuits by playing with it. Our intervention was about 90 minutes long. Most of it was kind of done around the craft. And we did do about 5 minutes of lecture just to kind of introduce the language and the big ideas and to make sure that the kids could map what it is they were experiencing, that sort of tacit, playful kind of experience, into something else larger. And so as the kids are engaging in these littleBits, you can start to see when you're talking and experiencing something that's well aligned, you start to remember it. So these things of how these things kind of hook together. So in just over an hour, we started to see proven increases in these 3 concepts of circuitry. So this is the connections we were talking about earlier. The kids started realizing that, circuits don't work if you don't have things correctly connected to each other. They can't just sit next to each other. It's not like a Wi-Fi signal. The current actually has to flow through these solid connections. So on the pre-test, before the kids had any experience with littleBits, they just sort of put all of the objects next to each other. They weren't really aware or looking at the metal pieces and how the metal would touch, or thinking about how those things had to touch each other. You could see them kind of thinking, well, plastic is conductive and metals are conductive, so it doesn't matter. Maybe even the glass light bulb could connect. But after working with littleBits, they start to understand that they have to start to think about how closely things are aligned and the connections there. Polarity, in littleBits' choice to kind of avoid the traditional light bulb that has no polarity and go for the LEDs and other kind of directional kinds of outputs. Now all of a sudden the kids are experiencing polarity. You've probably seen them get the LED turned the wrong way, but it's not just that it's turned the wrong way, it's now all of a sudden those magic magnets are pushing back on it. So they have like an embodied experience about pushing away that was not the correct solution. So without you having to speak to it, they're experiencing it. And then they also have that magic suctioning that sort of happens when you get the magnets turned in the right direction. So now all of a sudden they're starting to think, actually, oh wow, this kid, is starting to tell me that direction is important. And then lastly, this idea of current flow becomes important, so that the current has to flow in a circle. When you look around your home, when you look around other things, a lot of misperceptions that kids have is that they'll plug something in and the light bulb will suck all of the juice out of the wall and put it out into the air. So this idea of electricity of just flowing one direction and kind of coming out of something, kind of like a water faucet, is sort of what they understand. But after playing with littleBits, they start to see, oh, actually there's 2 magnets, and they could flip it over and they can start to see the path that the current would take. They start to kind of be able to understand and kind of envision within the technology where that lies. And that's not true of a lot of toolkits. The other things that we learned is that these are challenging for kids of all ages. So these same competencies that are learned by youth using littleBits, as we mentioned before, are sort of challenging no matter who is engaging in this. We've worked with teachers that have used the traditional toolkits and had all these misconceptions about how circuits work. And now all of a sudden when we introduce littleBits, all of a sudden they start to realize, oh wow, actually this is the way it works. I've had PhDs in physics. I've had the president of the robotics club for 4 years come and use these tools. Now all of a sudden it's reformulating the way they think about these things. We also found that there was no real differences by age or gender in the learning results. So it didn't matter whether you were in kindergarten or whether you were in 8th grade or whether you were an adult. You were having access to these big ideas that are really, really important. So that, when we start to look at that, what does it mean to not have these persistent misperceptions of any type of science, but of circuitry really early on in your life? So now all of a sudden you can start to build on that. So when you get other kinds of circuitry or STEM or CS kinds of interventions, now all of a sudden you're able to understand them, because it wasn't just a magic, you happened to get it right and get the light bulb on. You've actually really engaged in the conceptual content. The other portion about littleBits is that we saw no differences between the girls and the boys. And that is really rare as well. They equally liked it. They saw it for boys and for girls. It was the only kit in the market that we saw that kind of gender neutrality about. So that was exciting as well. So this kind of all brings us back to kind of thinking about Seymour Pappert's work. And for those of you that don't know Seymour, he was out of the MIT Media Lab and was working, sort of in the late 70s and the 1980s. Maybe you grew up, playing Logo on your computer. Seymour was really the visionary that kind of said that computers were for kids. Back when computers used to occupy whole rooms in a building, he was saying, they needed to be desktops and every child needed to have one. But he also kind of famously said, it's not the computer that needs to program the child, but the child that needs to program the computer. And so really trying to think about flipping that. And so this is one of the quotes that we love about, we need to produce people who know how to act when they are faced with situations for which they're not specifically prepared. So Seymour, really kind of knew that it's not just about what we're doing in our classrooms or in our after-school settings. It's really about what happens next. How do we prepare them for the unexpected? And this is, the one key thing that we keep finding about littleBits is that it really helps to prepare the kids for those future experiences. So we're really excited about that. But what that means is that when kids come back to it in the future, when they start building on these things, is that they have a really solid foundation, that they've learned something substantial. And then, as we go into IoT and sort of wearable circuits, all of these kinds of things, how do we start to know and understand the world around us? It's not just a mystery, it's not some magic that's happening, but that these things can be created and that they're made from similar kinds of parts. So it's really fun seeing kids, play with these electronics and then all of a sudden understand that actually the whole world's made up of these little bits. It's pretty exciting. So design matters to make kids successful in circuitry learning. So, students working with littleBits, we just mentioned that they scored significantly higher than students working with the traditional kits in their circuitry knowledge. And we started looking more closely at sort of the littleBits and the design of these toolkits about sort of what made them so special. What could other designers start to know about these kits and what's working and why? And these are kind of three things that really kind of solidified for us, is that littleBits is intuitive, but not too intuitive, and I'll tell you why that's important, is that you can pick them up. When I have a table and I have all of the toolkits out there, I'll tell you the one that they gravitate towards the most is the littleBits. They can pick it up, they can start to play with it, they can start to see how it works and move things together. I love the Korg littleBits, the other portions where the kids are producing music, and a lot of the advanced bits as well. But because they just, there's a way of just engaging in them that sort of leads to later exploration. The kids, there are some helpful projects, but you see the kids deviate from them consistently. That's not true of all of the toolkits. A lot of times they're only proficient in using the toolkit if they follow exactly the directions that are provided, and they're not able to innovate. Even after they make 100 different projects, they still don't have this conceptual understanding that littleBits really offers. The magnets also provide this sort of instant feedback. And this becomes important because there's a lot of ways to make a connection. We showed the alligator clips. There's the snaps. but the magnets and that magnetism that pushes and repels, as well as sort of snaps the circuit together, becomes really important for kids to kind of understand that those things are there. It's also kind of fun to take an everyday object like a magnet and say, wait, that can actually conduct electricity in this way. And so I think it also gets kids to think a little bit more about the world around them. It's not some specialty, alligator clip that they only see here, but they can start to say, oh, this magnet's conductive. And, and many of the other pieces will kind of, I've seen kids take paper clips, for example, and start to link their little bits together, for example, different things like that. Gets them to sort of innovate and become inventors with these things. And we did not find the same kind of thing and the same kind of learning gains for other kits that use snaps, for example. And then the third component is the littleBits design demonstrates circuitry basics, so that you can really start to see it's that visibility into what the circuit does that becomes important. It actually becomes important that the kids can see the back of the bit, that they can kind of trace and see how the bit was made. There's a lot of conversation in our workshops about those kinds of things, and that kind of transparency becomes really important to this work. And then lastly, you're going to start to see, you can start to see, how these things start to put together. As you know, sort of the color coding of, sort of think about power and input, the wire and logic and output, that the color coding becomes meaningful. And you see this kind of used in several different learning technologies, but used really well. So it's a choice of colors that littleBits has chosen, that kind of indicates that sort of gender neutrality. But it also, as these bits snap together to make larger circuits, these new concepts are easily transferred to new littleBits kits. Or an invention that a student hasn't seen before. So they don't need to relearn the basics of circuitry each time that they play. The power and the outlet, they keep using the same one. It doesn't look different as they move through the system. That the outputs is that, the bar graph and the LED, you can start to see how these things start to increase in complexity, or how there's a whole choice of different input devices as well. And so the kids start to see larger classes of things. Oftentimes, colors not used in this way. Oftentimes, that you don't see a consistent attention paid to these kinds of things. So this is a closer look at those magnets and that physical feedback that we were talking about before, that we started to see. So that, that wasn't just a random choice, that becomes really important design decision that really outweighs every other kind of way of making that kind of magnetic connection. And, we went through the sort of the circuitry basics. So as you start to think about sort of the designs, this provides an alternative entry point for all kids. So we have this sort of gender neutrality by design. So a lot of our work, we're in after school centers, we have kids opt in. And it was so funny when we had the traditional toolkit in there, the girls opened the door, saw it there on the table, and immediately closed the door and left the building. They're like, no, this isn't for me. Just by looking at it, it was like in 10 seconds, they'd already made that decision, right? And, we think in classrooms, they don't have a choice to opt in, and that can be good. But if you know this is happening in the out of school hours, they're going to continue to opt out later on. But the fun thing is with littleBits, you don't see that at all. You see girls and boys equally interested in playing with these things, and sort of learning through playing. And so, we also didn't see any differences by race or ethnicity as well. And then, it's not just about doing sort of these kind of STEM areas inside of school, but outside of school becomes really important. So these non-compulsory settings, if you want kids to kind of, commit to the 10,000 hours, they've got to find a toolkit that's for them, something that they want to continue to play with and have more access. So in summary, it's an effectively, littleBits are an effectively designed circuitry toolkit that puts complex topics into a real world and playful context. They have an intuitive design, and they're equally appealing to both boys and girls. We want to open it up for Q&A because I'm sure you have a lot of questions for us, and we would love to kind of tell you a little bit more about the work that we're doing and sort of what's on the horizon, and sort of any more information that we can share. We'd also love to learn from you and sort of what you're doing in the classroom and what you've noticed and seen too about learning. So I'll pause there.
Thank you so much, Dr. Peppler and Naomi. I do see a few questions here, and I think we can address them now. Just a quick clarification question. Did the traditional toolkits that you explored in your research have elements such as motors, 7-segment displays, buzzers, anything like that? Or were they just the 9-volt battery, Alligator clips, and the light bulb?
Correct. We are, you'll start to see us, it was just the basic kit. And you'll start to see us sort of move into other components of the system, but we didn't want to add too much complexity there before kind of understanding how everybody just did basic circuitry with their kits. And you could see it's kind of challenging then to say, well, what did kids learn if we add lots of bits into that initial experience? But we know we do have some hypotheses that littleBits is really good at things like prototyping, for example, and teaches a lot of other concepts really well as well. There's a lot of kind of unique bits out there that you don't see in other toolkits on the market.
And I'll also note that we tried to make sure we had a parallel set of materials in each one of the kit groups. And so if we had a sort of a switch and a buzzer and a light in one kit, we would make sure we had the exact same types of things in each of the other kits.
And Naomi, it might be worthwhile kind of sharing a little bit about kind of the next stage studies and some of the things that we're looking at now that are on the horizon.
Yeah, we're starting to think about sort of what types of materials help afford creative circuit design. And so where a traditional kit might also involve, we're starting to move forward into things like breadboards. And we think about the types of designs that we're able to make on top of a breadboard. And then when we're able to expand into different directions, like with littleBits or different layers, we're starting to think about how that might support sort of more creative types of designs.
That's great. Another question from the group, can you share, are you willing to share the specific kits that you were using from each of the companies that you've outlined here?
Sure. Naomi, do you want to share?
Yeah, so I believe, here, I'm looking back. Well, I think the traditional kit we got sort of from a standard sort of school supply company. And so that one, Alligator clips, and I think that type of kit is sold in several places. With littleBits, we just used the sort of starter kit. With snap circuits also, we just used the starter kit, although we didn't use all of the pieces. We didn't use the sort of soundboard that's a little bit like some logic involved in that. We didn't use that. Squishy circuits was also the starter kit. This was a few years ago. I think the kit they have now as their starter kit is looks a little bit different, but essentially it was just the light bulbs and the dough and the battery. And we sort of used dough to make its own type of switch. And then with LilyPad, we used I think we used SparkFun as a supplier, and then essentially it was the same types of materials, thread and a switch and a light. And we actually didn't use the coding, sort of the Arduino piece in this kit, because we were just looking at the sort of basic circuit, the sort of simplest type of kit. But we're sort of moving into that now as we look at circuit design.
And all of these kits, what we do is, we're working with large school districts, or we're working, in New York City or in Pittsburgh, and we kind of ask folks, so, what are you currently using? What are you thinking about purchasing, and why? And sort of what that sort of became sort of the focus of the research.
Great. So was age a factor in whether boys or girls were interested in the kits in this study? And also as a follow-on to that question, were there any verbatim taken from the boys or the girls on what they liked or they didn't like about each kit? We've had a few questions about why some of the girls thought that the kits were not for them when they took a look at them.
Yeah, that's a great question. And actually, Naomi has been following up on that and looking at that a little bit more closely. So, Naomi, I don't know if you want to pull up any of the quotes from some of the folks, but you know, what we're finding is that the materials that the kits are made of, surprisingly, it's not all about the color, but it's really the kinds of practices that you're engaged with. The extent to which the girls could start to do anything that they wanted, sort of being able to sort of pull in the arts and kind of envision something and then have the toolkit create that thing. So if you think about like the traditional toolkits, it's hard to like hide, you know, this like huge 9-volt battery in this blue case. You can get creative with that, you know, and you can kind of encase it in different things. But it feels hard to sort of handle. It doesn't feel playful. It doesn't feel like I can make that part of the work that I'm doing. And then, we wanted to share a little bit more, because what we did is we interviewed both the girls and the boys, and you know, kids of all different ages, about sort of which kits they thought they would play with and why, and you know, why would this, if they wouldn't play with it and it was for kids of the opposite gender, why was that? And so we really tried to understand more of this kid's perspective on the kits that they had. So Naomi, why don't you say a little bit more about some of the work that you've been studying?
Yeah, and so we asked the kids questions such as, like Kylie was saying, would you play with this? Why or why not? Who do you think is supposed to play with this? What about this makes it, you know, for whom? And we saw some interesting questions. We noticed it was a lot more about the practices and what's done with each kit rather than what it looks like. And so we were less likely to see things about, like Kylie said, the color. We were more likely to see things about what you do with it or how it acts. And so in the case of e-textiles, we did see some responses like, well, I think this is for girls because more girls sew. Sewing, the practice of this is a girl thing. We also saw the opposite sort of with the snapping. We thought some kids thought that snap circuits sort of made them think of the types of things that you snap together like blocks, and that's something that boys are more likely to do. We also saw, just kind of based on experience, you know, I see more boys play with stuff like this, and so I think it must be for boys. There weren't a lot of girls in my class that liked circuitry, and so I don't think this is for me. And those were kind of what we were saying. Of course, we also had some kids who were thinking, well, I think everyone can do everything. And of course, we completely agree with that. But we also we wanted to see what kind of identification they were having. If they don't think that it's something that other people like them might be interested in, or they don't think it's something that was made for them and made with them in mind, then they're more likely to disengage with that. And like Kylie said, you know, sometimes even just walk out of the room when they have the option to.
You did have another question about sort of whether that varied by age, and we didn't see any variation really by age and gender. You know, the girls that walked out were still kind of, you know, early elementary school, you know, kind of before these very gendered perspectives start to appear kind of in middle school or some whatnot. So I think all of this sort of happens much earlier. You know, sometimes, you know, this is a space, you know, it's a boys and girls club, you know, where there isn't, you know, like we were going in to do the research and we were working with folks there, you know, so if you're an educator and you know how to build that rapport with kids and sort of build that trust, right, you could sort of start to bridge that gap for the kids, right? But there's something you're kind of fighting against initially, I think, in the choice of the toolkit that could either work for you or you can start to work against it. And some of the kits, you know, also had the challenge of being really super girly. So the boys didn't think it was for them, you know. So littleBits kind of being right in this gender neutral sweet spot, you know, kind of creates a really you know, productive context, you know, for a high quality educator to enter into and start engaging this large group.
Then as a follow-up to that question, are you planning to do a longitudinal study to see if the littleBits girls developed an interest in science and maybe they were less dissuaded by the wires and the alligator clips?
Yes, yeah. Well, and that's actually the funny thing is we are actually we have some funding from the National Science Foundation and the Wellcome Trust right now, and our partners at the University of Washington are starting to do a longitudinal study around this work. So hopefully we'll be able to answer that question soon. But part of what we've observed is that when you have a first sort of safe experience in something, learning something, is that you're more likely to kind of venture out of that territory and kind of see through the veneer, right? And we can all accept that, like, there's nothing about a 9-volt battery that should be off-putting. It just is or it isn't, and that initial kind of emotional, judgment and close call that you're making there. So I just think, this is my hypothesis, but my hypothesis is that when you have a strong foundation like this, you pave the way for good high quality learning, but you get girls to kind of see beyond sort of the veneer of the toolkit and be able to see the kinds of intellectual possibility and the materials around them. I can speak from my own experience in the arts class, for example. So, I was like building and making things, but I never used power tools and huge table saws and all of this kind of stuff. So as I got into sort of advanced sort of sculpture classes in my undergraduate, now all of a sudden I had access to these things 24/7. I was welding, doing all these like dangerous practices for girls. But I started seeing them as for me because I was creating art. This is the art that I wanted to create. This tool was going to allow me to do that, right? It didn't feel girly or not, it just felt like part of the practice and empowering when I was able to do arc welding, and be successful at that.
Makes sense. Thank you. Okay, so we've been getting a lot of questions about cost. Newer toolkits typically cost more than these traditional kits that we're talking about, in these traditional kits that many educators already have on hand. So is it better for educators to use a traditional toolkit to give kids some hands-on experience, or to just use no kit at all because they might not be able to afford the new materials? Basically, how is cost factored into the research?
Yeah, we're trying to work on some policy papers to kind of bring the cost into the equation. And what I would say is go ahead and use the materials that you have at hand. We're really into sort of maker education. We work with the Maker Ed Network and partner with Dale Doherty and other folks in Maker Media. So you'll never see me say throw out those old tools. But is there any way to reinvent them in ways that make them not feel so precious, right? And looking for different ways to extend that toolkit. So you've got the 9-volt battery. You maybe have, it doesn't take much to make your own battery holder, right? You can, you could wrap it in tin foil and create 2 leads that sort of lead out of that. So I think the more you sort of make your pieces, pull from them, hybridize some of those existing tool sets that you have there, the more the kids will start to see into it. And I think, all of these new toolkits have come onto the market because makers have tried to integrate, many of these things there, blending new tools, but just using normal magnets and maybe soldering a wire to them, different ways that you can at low cost, sort of start to achieve these same kinds of things. That's why, we're trying to illuminate sort of the design principles, that you can start to use as you start to think about these kinds of things. But and it's not just about the kit in particular. These other kits have come down in cost because they've been on the market for years, and this equipment is aging and so forth. And so, I think that will change. A lot of these new maker toolkits are kind of new to the market, and so you see, and so does that market analysis. They're a little bit higher in cost, and they'll start coming down over time as well. So I think be creative, think about sort of the arts and science intersection with those kinds of things. Don't throw anything away. Think about how you can start to integrate it, or small things that you could purchase to start exploring that. And I guarantee you, email us, tell us what you've got, and we'll give you a couple ideas about how to extend that. We'd be happy to do that.
Yeah, absolutely.
What would you say is a recommended kit to start with for after-school classes? What age range does it cover? And also, what about people who only have a very short amount of time? What would you recommend there?
Oh my gosh, littleBits is for you if you only have a short amount of time. Yeah, you know, the fun thing is that because the kids can engage in the circuitry kit, all of a sudden, you know, it gives you lots of time to do sort of the aesthetic explorations, you know. So I think you have that. Naomi, you want to speak to some of the other parts of the question?
Yeah, absolutely. I mean, I think when we're thinking about age, I think part of that littleBits being intuitive and those magnets, I mean, I don't really think there's an age that can't start to play with circuits and think about that. So, I mean, even as young as preschool, nursery school, and we've actually done some of that work as well, playing with circuits with really young students. And so, yeah, absolutely. I think that especially when you're sort of working quickly and working with younger students, littleBits is a really great one. Yeah.
Yeah, and I think, you know, I think that, you know, we tend to use sort of the basics littleBits kit and then kind of start to augment things, you know, over time. But that's been really effective to kind of get people going. But think about, like, you know, just having a few different output devices, a few different input devices, different ways to sort of connect, you know, those input and output devices. You know, sometimes even sort of working with batteries where you can stack, you know, 3-volt batteries. You know, there's a great vendor who sells those 3-volt coin cell batteries for about 25 cents a piece, for example. And what's kind of fun there is that kids can build their own batteries, so they can keep stacking the 3-volt batteries, you know, from 3 volts to 6 volts and 9 volts, and start to see the impact on, you know, how bright the light bulb will burn, you know, how many LEDs that you can put in series as opposed to parallel, right? Mm-hmm. So, you know, I'm teaching a class right now for you know, senior undergraduate majors in informatics and computer science, and we still are going through the basics of circuitry, as you might expect, because they didn't have these kinds of toolkits growing up, and so all of this becomes really important as they start to see through these things. You know, LEDs, when you buy them in bulk, especially, come down to 1 or 2 cents a piece. So, you know, just kind of you know, creating a simple problem, having lots of those devices, you can start to see people do all sorts of fun things with littleBits. So even if you don't have enough money yet to buy all of the advanced bits, you can start to hybridize your kits and you know, get them to play with other kinds of connectors and, you know, other kinds of outputs and so forth. And so you can be very creative with even your base kit.
Yeah, and I'll also say an after-school setting is a perfect place to start playing around with some of the making and design that we were talking about. You know, recycle materials. When we're doing a workshop, I just sort of lead up to it and save all my cereal boxes and things like that, and just bring them in, and that's, you know, extremely low cost. And then it invites students to sort of think imaginatively about what types of circuits they're making and why.
Yeah, and another fun thing that I do is, like, just buy one multimeter, right? You can go and buy one multimeter for like $35 or something. You know, go to the SparkFun website, and it's just multimeter. If you've never used a multimeter before, you can turn it into the little continuity mode, and you know, you can take your little 2 prongs around the house and into your drawer and over to the craft store, and you know, you can test things to see if they're conductive or not. So you can test all your recyclables. You can, you know, I just had a fun time. You know, we just played this like Jeopardy game on what's conductive and not conductive. And I just grabbed all the kids' toys, you know, the plastic, you know, beauty queen crown, you know, kids were guessing was conductive because it looks like metal. No, that's plastic. It's not conductive. You know, the Altoids tin, not conductive because it's insulated with some sort of plastic coating on the outside to keep it from the paint from chipping off, you know, but it is magnetic, you know, so all of these things are kind of interesting, you know, as we start to think about how the materials around us are built. So that's kind of one way, you know, and you know, you could use one multimeter, and I had 100-person class, you know, we just had Jeopardy teams, you know, just guessing whether something was conductive or non-conductive, and got points as we moved on. So, you know, so whether you've got small groups or big groups, you know, there's kind of ways to you know, help to introduce these concepts to that group.
Got a lot of interest in the multimeter when you mentioned it. So I think that we don't have time for any more questions. But I would like to invite everyone to reach out directly to the littleBits team. You can email us at press@littlebits.com. We're happy to forward any questions to Kylie or answer any additional questions that you might have that were not addressed today. I just want to thank Dr. Peppler and Naomi. Your research was really intriguing, and thank you for presenting it for all of us today. I want to thank the audience for your great questions. We hope to hear from you with any follow-ups that you have, or any great experiences or not so great experiences that you might be having in the classroom. We're partners in this, and so we're looking forward to all of your feedback. Thank you all for your time today.
Thanks so much.
Yeah, thank you for having us. It was wonderful to be here with all of you, and we hope that you do some fun things with your youth, in the next week or so.
And your multimeters.
and your multimeters.
All right, thanks everyone. Have a wonderful evening.
Okay.
Bye.